back with another upload. I know I haven't uploaded in a really long time, but today we're back, and just like I promised, we're going to do our first silver problem walkthrough. So today we're going to be working on the 2019 January contest, and we're going to be doing the third problem in the silver division contest, Mountain View. Now, again, as I've said this for all of my videos, without further ado, let's get into it. Alright, so if you want, you can pause the video right now and read the problem, but basically the general gist of the problem is that we basically have an XY plane that acts as Bessie, the cow's field of view. And in this field of view, she's going to look at a wonderful view of a mountain range on the horizon, and in which there are n mountains in the range of 1 to 10 to the 5th. And if we think of Bessie's field of vision as an XY plane, okay, we already mentioned that, then each mountain is a triangle whose base rests on the x-axis. That's how we know that each mountain cannot go below the x-axis. So this is going to be the lowest point here. Draw an arrow there. And if the two sides of the mountain are both at 45 degrees to the base, so the peak of the mountain forms a right angle. Okay. So we know from this statement that any mountain is going to be a isosceles, a right triangle with 45, 45, 90 degree angle measures. So it's going to look something like, hold on, I'm kind of bad at drawing. Let's see if I can draw a sample out here. Looks fine. Basically, each triangle is going to be a 45, 45 degree, 45, 45, 90 degree right triangle. So again, this is 90 degrees right here, and these two smaller angles are going to be 45 and 45. Alright, so the two sides are already did this part. So mountain I is therefore precisely described by the location x, xi, yi of its peak. So from this statement, we know that every mountain is defined by a coordinate, a set of coordinates, and only one. We don't have any other dimension, any other coordinates. We only have a coordinate of its peak. So no two mountains have exactly the same peak location, okay? So Bessie is trying to count all the mountains, but since they all have roughly the same color, she cannot see a mountain if its peak lies on or within the triangular shape of any other mountain. So please determine the number of distinct peaks and therefore mountains that Bessie can see. So we don't have to consider therefore mountains in this situation. All we need to do is determine the number of peaks Bessie can see. And keep in mind, Bessie can still see peaks that are covered by other mountains. So basically, let's just say that there's a big mountain right here, and there's a smaller mountain right here, but its peak is still exposed. So it doesn't matter if the mountain is in front of a mountain or behind another mountain. All we care about is the peak. So let's check the input format here. So the first line of input contains n, and each of the next n lines contains xi and yi, describing the location of one mountain's peak. So, okay, so 10 to the 9th. So this is a pretty large size, so we do have to limit our scanning of the data somehow later on. So please print the number of mountains that Bessie can distinguish. Okay, we got that from earlier. Alright, let's try to decipher the sample input here. So we have 3 mountains, and the peaks are described as 4, 6, 7, 2, and 2, 5. And in this case, the sample output is going to be 2, because in this example, Bessie can see the first and last mountain, but the second mountain is obscured by the first. Okay, so let's just see what this problem is trying to mean here. So you can search up any sort of geometry tool. I personally use GeoGebra. Let's get that going. And let's do start calculator. Oh, yeah, there we go. And if you go to the tools section, you can see that we have a lot of different tools being used to manipulate some geometry in this graph here. Yeah. Alright, so let's plot these points down. So we have 4, 6, 7, 2, and 2, 5. So, okay. Let's see. So if we click more, we should get a Polygon Tool. So, yeah. So let's find 4, 6 real quick. So 4, 6 is right here. So just about there. And how do we know how these triangles are going to look like? We're only given 1 point. Well, based on earlier, we know that they're 45, 45, 90-degree right triangles. So we know that each of its, say, legs are going to be y equals x lines, or y equals negative x lines. So again, the slope is only going to be 1. So knowing that, we can easily plot our triangles with ease. So we can plot it there. And next, just from here to here, we draw an imaginary line of a -1 slope. And that gives us our first right triangle. So again, we're going to repeat this process for the 2 other points. So we have 7, 2. So let's find the point 7, 2 right here. And again, we're going to make right triangles. And GeoGebra is really great because it kind of senses what you're going to do. So like right now, even though it looks like I'm being really exact, it kind of like allowing me to pinpoint those points. And we have 2 to 5, which is our final triangle. So let's find 2, 5 right here. And again, has to be a right triangle. Okay. And from here, that should be good. Right. All right, so let's see what this problem is trying to say here. So it says in this example, Bessie can see the first and last mountain. So remember, the first and last are 4, 6, and 2, 5. And in this case, that would be correct because this big one here is the first one. The last one is the one to the left. And the second one is going to be the small one right here. So the second mountain is obscured by the first. Great. So we pretty much envision how the mountains are going to work. So now it's time to think about how we're going to implement this into code and basically trying to solve the problem and how it works. So the first thing we're going to do is find out the criteria for whether a triangle is obscured by another. So let's just say we take away this triangle right here. Let's delete this point. So now we have a small triangle that's clearly obscured by another. Well, in our code, we're going to basically do a method that basically compares 2 triangles and finds whether one's obscured by the other. So we can say eliminate that one, knowing that Bessie can't see it. So what's the criteria? Well, as you can see, basically, if you look here, you can see that both of these dimensions are obscured, are smaller, and how do I say this? So let's just say this left coordinate for its left leg here. We know that this has to be greater than a bigger triangle's left dimension or left coordinate. So we know that this point, this x equals 5 point here, has to be greater than has to be greater than this big triangle's -2, 0 coordinate, because we know that these triangles are always going to be in 45, 45, 90 orientations. So that means we can't have a triangle that looks like this, or we can't have an obtuse triangle that looks like this, where even though its coordinate is within, we can this could be like out or something like that. But basically, we know that these triangles have to be 45, 45, 90-degree triangles. So we can sort of cheat our criteria a little bit. So since we know that these dimensions, this dimension is always going to be pretty much the same, like the triangle can't be oriented like this, we can just use these 2 points, like the bottom 2 points of every triangle, to describe to know whether it's within another. So for example, the final criteria is, let's go back to our whiteboard here. So how to determine whether a triangle is obscured by the first? Well, it was a big one and a small one, and that's just if these 2 points of a smaller triangle and these 2 points of a bigger triangle. So we have to compare these. We compare this one with this one, and this one with this one. How do we compare these? Well, this one has to be greater than this bigger triangles. So in this case, this has to be greater. So this greater than sign. And we know that this coordinate right here has to be less than this bigger triangle's outer coordinate or dimension, whatever you call it. So this has to be smaller. And that's how we know that a triangle is completely within another, because, well, first of all, the peak has to be within the dimensions. But basically, if we know that the triangles, two like bottom coordinates or leg coordinates, I don't know what to call them, are within another triangles, then we know it has to be covered by it. So now that we sorted out the criteria for whether a triangle is inscribed within another, or not inscribed, or is covered or obscured by another, we can begin our thought process for how are we going to implement this into code form. So let's open up your IDE real quick and let's get coding. Alright, so I've booted my IDE here and IntelliJ, and what I've done is that I've basically just copy and pasted my buffer reader and pre-writer statements just to read it in the input, and also print out an enter file to the USACO website just to turn it in. And I've also created an integer n, which, as you know, is going to be the number of mountains in the first part of the input. So we've processed one part of the input. Now we need to process the mountain coordinates. Well, before we can do that, we need to create a mountain class. And we're creating this class because if we create any other data structure to hold these coordinates, it's probably going to time out. So let's create our mountain class right here. Alright, so let's see here. Let's do static. So under the main statement, we can do static class mountain. And because we need to compare these mountains with each other, basically based on their coordinates, and see how they basically obscure each other, and at the end of the day, which one's Bessie is going to be able to see, we need to implement a comparable class, which is going to allow us to compare mountains with ease. Alright, so let's do mountain, and let's go public. Oops, did I do something wrong here? Okay. So yeah, we can also do the default compare to class, but we're probably gonna change this to something else. And alright, so we have to establish our global variables, so public int x and y. So again, these are going to be the coordinates that describe the mountain's peak as given in the input right here. So let's go back to our IDE. So if now we have to establish our constructor, which is going to basically just tie in all our variables and the class name, and initializes the class. So since we use the same variable names, let's go this dot x equals x, and this dot y equals y. Okay. So now we need to fix up this compare to method here, because we're not going to return 0 when we're comparing mountains. Let's see here. We need to compare. Let's see. So how are you going to format this? I see. Okay. So first of all, we need to sort the mountains based on their height, which is the y value. Again, this is y, this is x, because again, the tallest mountain is never going to be obscured by any smaller mountains below it. So therefore, we need to sort. Let's sort the mountains in descending order. So just so we know, the first one is not going to be obscured. So let's do that here. But again, we need to compare mountains by height, because we know that all of these are going to end up looking like 45, 90 degree triangles. So sorting by height will enable us to basically see which ones are obscuring which in an in order fashion. So let's go return. Let's see, mountain y. Okay, mountain m. Sorry. So let's do compare. Return integer dot compare y m dot y. And this will allow us to compare, or basically sort these mountains based on their y value or their height, which will allow us to find the tallest peak and go down from there. So now that we've done that, we need to declare, like I said before, a method that's going to allow us to check whether a mountain covers another one. And again, the criteria that we worked out is that a mountain covers another one if the smaller mountain's dimensions are within the larger ones. And because these are 45, 45, 90-degree triangles, that's all we need to check for. There's no other way that the triangle could be visible, or the peak could be visible to Bessie, if the dimensions are within another one's. So how do we check whether one triangle's dimensions is within a larger one's? Well, again, that's just a matter of the mathematical coordinates. So basically, we can mathematically compute whether these coordinates is within this larger one by basically taking the difference of the two and checking whether this one is greater than the larger triangle's left dimension, and this one is smaller or less than the bigger triangle's right dimension, or right coordinate. Sorry. So yeah, that's going to be the criteria that we're going to do. Okay, so let's get started. Let's get started creating this method real quick. So let's just do a static boolean, because again, it's going to be a matter of yes or no. Is the triangle covering another? And let's just do mountain. Let's just do A and B for simplicity. And let's create some variables real quick to represent, again, the left point, the right point for both triangles. Oops. Let's call it covers. Just so like another triangle covers another. So let's create some variables here. Let's do int a left, and okay. So I've cleared my sideboard here, but again, oops. We have two triangles, and a left is going to be let's just say this triangle A, this triangle B. So a left is going to be a left point, or a left leg, end point, I don't know what you call it, of the smaller triangle. So this is a left, or AL, and this is A right, and this is B right, and this is B left. Alright, so we need to establish these four variables, but again, how do we calculate them exactly? Well, since these are 45, 45, I need to give it better drawing. So since we know these are 45, 45, 90 triangles, we need to find these coordinates right here, or these points. Well, how do we do that? All we're given is this top coordinate right here, or the peak. Well, because these are 45, 45, 90 triangles, we know, first of all, doing some math, we know that these two angles are 45 and the same, and therefore we know that these two sides are also the same length. So how do we find from here? We can draw a line just to sort of gauge the distance between this coordinate, or in this case this x coordinate here, gauge the distance between the x coordinate and the leftmost and rightmost bound. Well, in this case, we can do some math, and basically, because we split this in half, this is also 45 now. These both are 45. Well, now these two sides are also congruent, and this is just the y. This is just the y value. So I've drew a better example over here, but basically you can see that the line from this vertex to the midpoint of the hypotenuse is going to be exactly congruent with these two. Or here, if I put up a screenshot real quick, yeah, let's just do another one real quick. If we screenshot this real quick, we know that this length is x, this length is also x, but this length is also x. So in this case, it's going to be 2x plus the entire thing. And from this, we can calculate the exact distance between the midpoint of this to the right bound and the left bound, and this will allow us to essentially calculate these bounds and compare them. So yeah, so I had a previous screenshot, but I ended up botching the explanation. So this is my second time recording this, but it's nothing of the matter. But basically, let's establish our variables now. So equals a.x minus a.y. So an a right is going to be a.x plus a.y. So again, if you guys don't understand why I'm using these expressions to represent these variables, again, if you go back to your Zeitboard, let's take another screenshot of this just to explain it better. Again, let's just say that this is so. Let's just say that we have a larger triangle here, and this is triangle A, and this larger one is triangle B. And we're doing the A bounds right now. So this is A left, and this is A right. So how do we calculate these based on the only point we're given is the peak, and this peak is defined by an x coordinate and a y coordinate. We know that y is 6, and this x is going to be 4. So how do we calculate A dot right? Well, in this case, we know that because these two sides are congruent, this is going to be 4 plus 6, which is 10. As you can see here, it's 10 right here. And this is going to be 4 minus 6, which is negative 2. And in this case, you can see it is negative 2. So that's just the general logic for calculating the bounds. All right, so let's calculate the bounds real quick. So, and B dot right, left, and B dot right. And let's just fill in these expressions real quick. Equals B dot x minus B dot y. Sorry, these are not supposed to be dots. And then B dot x minus plus B dot y. And then if B left is less than or equal to A left. So again, this is the logic that we established previously. Oops. And B right is greater than or equal to A right. Return true, in which or B covers A. And now let's return false. All right, there we go. That's the finish of our method. So now that we have our mountain class implemented and the method that checks whether a triangle covers another, we can begin our general loop to just in general for solving the problem. Also, I'm going to uncomment all this I had earlier, which basically just reads in the input as static class. Hold on. This should be allowed there. Let's see here. Static class. Static class. Let's see, which one is this? I think. So that goes there, that goes there. Do we need another one? That's the main. Oh, I think we're just. Okay, we're missing another parentheses here. All right, there you go. So I think from there we can make this static, and yeah, that works. So yeah, I uncommented a lot of this, which basically just reads in the input. So pay attention to how I read it in. I read it in as an array list, because for an array list, I guess it's easy to manipulate the data and like stretch the size more, I guess. So it's better as you go from bronze to silver. I think it's better to use like more complex data structures such as array lists instead of arrays. But that's just I don't know, my matter. But yeah, so I read it in as so x and y are the two coordinates of the peak, and you don't have to say egg. I just put egg down because it's kind of funny. But if you just say mountain M, or we already have mountain M there, but we say mountain M1, oops, and M1.ag. So, oops, here we're just adding in a new mountain given their coordinates. So now we'll end up with an array list stored with mountain objects. So, and each mountain is defined by an x and y coordinate. And we're comparing them with their y coordinate, or how tall they are each. So, since we're done reading the input, we can begin our just general process of solving the problem. So, let's see. So, let's go back to the drawing board real quick and the general gist of how we're going to solve this problem. Let's see. Okay, so let's just zoom out of that. So we're going to first have a count variable that's going to track our number of mountains best you can see. Mountains visible. And next we're going to use our array list, which is full of mountains, and we're going to sort it in reverse order, or descending order. So the biggest mountains to the smallest mountains. Okay, and then next we can, let's see here. So given, alright, let's just draw out some mountain examples here. And so they're going to be smaller, largest to smallest. And these are all mountains. So if we loop through this, we can use one mountain, and we can individually check whether this mountain covers another one. So we can check if this mountain covers this, it covers that, it covers that, and then we can move on to the next mountain in a loop in this in-order fashion. However, to minimize our time complexity that's spent on this, we can also establish a flag system, which is going to allow us to tell whether a mountain has already been covered by a previous one. So let's just, and what I mean by this is that Bessie cannot see a mountain if it's covered by any other mountain. It doesn't have to be covered by two mountains. It doesn't have to be covered by a certain mountain. Just one mountain is enough for Bessie to not be able to see it. So let's just say that this mountain covers this mountain right here. But this mountain also covers it. Well, it doesn't matter if this mountain over here covers it, because the larger mountain already covers it. So we can flag this, and basically for mountains down the line, we don't have to check whether this mountain covers this, because it's already been flagged. It's already covered by another one. So by establishing this flag system, we can really minimize the amount of mountains we have to go through. So let's first establish our flag system here. And a flag system is something I use that's pretty prevalent throughout my USACO journey. So I highly suggest you guys appropriate or adopt this method as well. Oops, let's go flags 0. So now we've basically set all of the flags in our array to not covered by any other mountain. So int count equals 0. Equals n, and again we have to sort our mountain array list in a descending order, or biggest to least, or greatest to least. So m, and then collections dot reverse order, and from there we can go for int I equals 0, I is less than n dot size, I plus plus. And if flags I equals to 1, you can say continue. And from there, so again, we're just going down the line of our mountains. And from here, we can go our individual loops for each mountain and check whether this mountain covers each one, and then we can flag the ones that it covers. So mountains down the line do not have to get compared to it. So for j equals I plus 1, because we don't have to check whether a mountain covers itself, we can do j is less than m dot size, j plus plus, and if flags j equals 1, or if it's already been flagged, then we can say continue, because we don't have to check it anymore. Same goes for the above if statement. Alright, so from there we can do another if statement. So if cover m.get covers. So now we're just using our method that we cleared down here to implement this system and checking whether a mountain covers another. And from there, we say m.get I. And then we go back and we can say flags j equals 1 and count. Oh, I see. Yes, yeah. So because we established count as n, basically all the mountains are visible. If we see that a mountain is covered by another, we have to subtract that count. And by the time this entire loop is over, only the mountains that are visible are going to remain. Every other mountain, if it has been covered, we subtract it from this total count here. So this count variable isn't actually established honestly at the beginning, but at the end it's going to give us a true answer. So from there we can print, just to finish off this, I guess I would say pretty hefty program here. We have to print out our answer, or the count, and then PW close and BR close. And yeah, there we go. So that was Mountain View 2019 Jan server. So I think now it's a good time to plug this into our online grade server and see how we did. So let's go. Alright guys, so I'm on the USACO website here, and I just plugged in my program, and let's see how we did. So it's taking an awfully long time, but it should be good. Alright, so 5 test cases, 7 test cases, 9, 10, and 11. So yeah, 11 test case problem here, and we got all of them correct with just a simple flag system strategy, as well as a method that checks whether a mountain covers another. So that was Mountain View. That was Mountain View. The problem, the 2019 January silver contest. So there. Hope you guys enjoyed the video. I know that my commentary has been pretty shaky this video, and has been for I guess my entire channel, but it's good to be back and uploading. So I'll continue to upload silver content, as well as content of your requests. I'll take in some requests if you leave a comment down below. But yeah, I hope you guys have had a great Thanksgiving, and I'll see you in the next video.